So hi everyone. So we are going to spend like 20-25 minutes talking about BPF, iptables, and packet filtering. So before we start, let me introduce myself. So my name is Quentin. I work for Meta. I'm part of the Linux userspace team, which is a team focusing on promoting and contributing to open source projects. We've got people working on systemd, makeosi, CentOS, and much more. And I've been working for the past year on what's called bpfilter, which is a BPF-based packet filtering framework. And that's what we are talking about today. So quickly, I'm going to remind you some stuff about iptables, just so we start on the same level. And after that, we're going to talk about bpfilter, what it is, how it works, and what it can be used for. So Netfilter, iptables. Netfilter is a packet filtering framework in the Linux kernel. You also have like iptables, nftables, iptables legacy. So basically, what we need to know for this talk is nftables and iptables will talk with the kernel using netlink, while iptables legacy will use getSocket and setSocket interface. So Netfilter is quite well known. It's the standard tool for packet filtering and packet processing. And it's fun. I mean, it's well documented, it's well used. You can find people helping you with Netfilter when you need it. But the downside is that in 2023, it can be slow compared to the other tool we have. And if I'm talking about packet filtering and speed and kernel, obviously the other tool is BPF. So if we go back to around May 2018, Alexei has been submitting a patch series to the Linux kernel mailing list called bpfilter, which was basically a user mode helper. So for those who don't know, a user mode helper in the kernel is a kernel module that spawns a userspace program. It has some use case, but so far I haven't seen any other use case than bpfilter. So if you find one, just tell me. I'm curious about that. So it was basically a user mode helper with some code to send the arguments of the getSocket and setSocket code from iptables to the module. And apart from that, it was doing absolutely nothing. And then around August 2021, Dmitry submitted a new patch series, a V1 and then a V2, with an actual purpose for bpfilter. So it was using the content of the setSocket call to convert the iptable filtering rules into BPF program and loading the program into the kernel. So after the V2, there was no update from Dmitry's, and they moved on. And I took over the patch series by the end of last year and submitted a V3 with improvement on the BPF bytecode generation and new features and stuff. And since then, a lot has changed on the project. And I'm going to teach you a bit more about what it is now and what it looks like. If you know about it, if you've seen the patch series and if you had a look, you would see that bpfilter from the mailing list is kind of like a backend for iptable. You've got iptables, you use it, and it's going to like give you performance and BPF program for free. It changed a lot since it was submitted to the mailing list. And now you should see this more as like iptables is a front end you can use with bpfilter. And bpfilter itself is kind of like general purpose. Before we dive a bit more into what is bpfilter exactly and how it works, let's go back to iptable again. I guess most of you know what this iptable command line means. For those who don't know, we call iptables with -i input, which is the chain we want to add the rule to. The filtering rule would be in the input hook of Netfilter. And then we want all the packets using UDP and coming from interface ETH0 to be dropped. So when you call that command line, what happens is that iptables is going to do a setSocket call with the content, with the rules basically, in a specific format, and it's going to go all the way to the Netfilter subsystem and be converted and be stored in the filter table in the input chain. So that's the whole work iptable is doing, sending the rules to the kernel, which are then stored in the table. And then for each coming packet, it's going to go through all the rules in the input chain and apply the filtering. So if the packet matches the criteria, it's going to apply the targets. Here the criteria are UDP and ETH0, and the target is to drop the packet. With bpfilter now, it's slightly different. If you look at the iptable command line, you can see a --bpf. You can't do that with iptables. With the one you have, at least, it's a fork I've made to support bpfilter. So don't try this at home yet. Eventually, hopefully. So it's going to basically use bpfilter in the backend. And we can see that bpfilter, the green part, is in part in iptables and in part on the system. So we have the libbpfilter, which will be linked to the client, and it's going to help you sending the filtering rules to the daemon. So it goes through a Unix domain socket, and the daemon will then receive the rules, convert the rules into its internal generic format, create a BPF program for the rule, and then manage the lifetime of the BPF program. If we look into libbpfilter now, the purpose of libbpfilter is to make something very simple. It needs to be short, lightweight, easy to use. You don't have to think about it. All the heavy lifting is done in the daemon itself. And as you can see, that's part of the fork I've got to support bpfilter from iptables. And the very core part is the line with ret equal bf ipt replace, which is the call which sends the iptable data to bpfilter. And it's a one-to-one replacement with the set suckup call from the original iptable. It's using the same argument, well, just one, but the same data format and the same stuff. And it's like, just replace it, and it works. So what happened in the background is that libbpfilter will provide a client-specific API, so you can give it your data formats. You don't have to convert or change anything. You just give it your data, and the daemon in the backend will be able to understand that, move that into a generic format, and then use it. So once the data is in a generic format in the daemon, we'll go to the BPF bytecode generation. So that's the part basically where we write into a buffer BPF instruction one after the other, which are quite similar to assembly instruction. We'll see a bit later what it looks like, but it's very close to assembly. So you've got your rule. For iptable, the rules are, you've got your chain, the input chain, for example. And in the input chain, you've got a chain of rules, and each rules are of 0, 1, or more matchers, and a target. So the matchers are kind of like a criteria to match against the packet, and the target is what you should do if all the criteria of the rule match the packet. We've seen earlier, we've got match the UDP packets on ETH0, and we drop. So UDP and ETH0 are the matchers, and drop is the target. And you can assume you have like tens of those in the chain, and then that's what bpfilter is creating. So from your chain of rules, it's going to write assembly code with jump everywhere, with comparison, and then at some point it's going to either drop the packet or accept it and stop. So we've got a big buffer of BPF instruction. And the BPF program generated can have like packet counters, for example. It can support BPF function, BPF call, kfunc call, a lot of various features we have on the BPF side. And since quite recently, it supports BPF dynamic pointers, which are a way for BPF to access random memory area safely. So from here, what we can say that bpfilter is basically a compiler. You've got a filtering rule from iptable or anything else, and on the output, you've got a BPF program. So that's what it looks like. So usually when I talk about it, it's a bit confusing. Like, you create BPF instruction, but what is it exactly? That's basically what it is. On the left side is the code from bpfilter. So we emit a lot of BPF instruction into a buffer of memory. And then the program is loaded into the kernel and attached to a hook. And you can use the Sonar tool on Linux to access the program and get details about it. If you use BPF tool, you just do a prog dump, and you have the bytecode of the BPF program displayed. And the bytecode we have on the right is the bytecode generated on the left, and it is the exact same thing. You can see also emit fixup, which is slightly different. It's not as simply like writing an instruction into the buffer, because sometimes you need to say, okay, let's just quit the program. And to do that, you need to jump to an exit. But when you generate the program, you don't know where the exit is. So a fixup is just a way to say, I will just emit an instruction now, so I've got the instruction in the buffer at the right place. And eventually, when I've got enough information, I'll come back and update the offset with jump 2. So it works for function call, because you can define function, and bpfilter is able to create the program with function call to functions that are defined by bpfilter later. So we jump to the function to the right place when we know where the function is located. So when you use it, it looks like this. You call iptable with the --bpf flag, and then you can use bpf tool to list the program. We see a few. So I limited the number of bpfilter programs to 2, but what happens when you call that command from iptables is that you will have one program per hook per interface. So for iptables, if you got the input chain, for example, and 2 interface, excluding the loopback interface, you'll have 2 programs per hook, so 1 for each interface. So this way, if you modify the rules to apply a new rule to just one given interface, it's going to change just one program, not all of them. And you have to have at least 1 program per hook. So yeah, that's it. And all the programs are pinned in the BPF folder in sysfs. So you can close, restart bpfilter. It's going to be fine. The filtering rules are still there, still working. From the performance point of view, I've run the benchmark a couple of days ago. So I've been using 2 servers with a switch in the middle with a 10 gig link. I'm using iperf3, and iperf was sending data at the rate of like 9.92 gigabits a second. And I've been adding from 1 to 256 rules, filtering rules. And the last rule was always dropping all the UDP packets on the 10 gig interface. We can see that if we got just 1 rule, it doesn't change much compared to iptables. It kind of makes sense. The hook for input in that case is located just at the same time as the iptable input chain. So it's running just after. So at this time, you can't have 10 gig traffic coming because you have all the kernel receiving packets, allocating the packet, and going through the network stack. So you lose a bit of traffic here. And it's the same speed, roughly, as iptables, because it's like 1 rule dropping packets. There's no complex computing to do here. BPF doesn't bring any performance improvements, really. We also have a cBPF program that I wrote myself, loaded into the kernel, and run the benchmark, which is slower. I don't know why. I don't know what happened. I'm going to send a message to Alexei soon to have some details about it. But I don't know what happened here. I'm a bit surprised about it. I don't have the cBPF program tested with more rules, because what happened here is that the rules are generated with a specific pattern. And if you write the program to filter yourself, you won't just check every combination of the pattern. You just write something that's smarter and check against the pattern itself. So it doesn't make sense to compare it to processing all the rules. So when we have more than 1 rule, we start to see the difference here. So on a 10 gig link for 32 rules, we can see that bpfilter is slightly faster than iptables. And when I say slightly, it's like 200 megabits a second traffic difference. And the more you had rule, the faster it gets. Well, the bigger the difference is. It's not faster with more rules, but the difference is bigger. for 256 roles, the difference in processing rate is like 2 gigabits a second. So to summarize this, I'd say that the benefits of bpfilter is that you have all the good side of having a BPF program, so the speed, for example, but on the other end, you've got all the ease of use and simplicity of iptables. You don't have to write or maintain a BPF program, which can be quite time-consuming if you got like 256 roles, 2K roles or more. And again, iptables is one of the ways to use bpfilter, but if you use a different way, then you don't have to use iptables. So currently, bpfilter supports iptables. It works with iptables legacy. It supports NIC filtering, source destination IP filtering, packet filtering, port filtering, sorry, protocol filtering. The bytecode contains functions. It uses dynamic pointers. It supports TC program and BPF Netfilter program. BPF Netfilter is quite recent. It's from a few months ago. It allows bpfilter to attach programs directly at the same location as the iptable hooks, iptable chains. So on the input hooks, forward, output, for example. So it doesn't have to perform like routing table lookup to know if the packet is located, it is aimed to the host or a different host. So, and it's a daemon, so you can have persistent filtering. You can stop the daemon, the packet is, the filtering is still here. And what I would like to do by the end of the year would be to support IPv6 to start working on support for Netfilter format. So right now it's iptable legacy, so it's specific format, and the non-legacy iptables and Nftables use a different format, which I would like to support. And I've got so much more to do. I'm barely starting. I can work on that for years. I've got my manager just here, so at least she's aware now. But yeah, a lot of things to do, so that's exciting. If you want to try it, feel free to go to the repository, clone it, fork it if you want, open issues. So the bpfilter repository is in the Facebook org. There is the bpfil tools repository, which is some random scripts I've been using and deploying on different servers, which makes my life much easier. But I've updated it recently, so you have all the details to build bpfilter and the fork of iptable, so you can try it out. If you run just bpfilter and you don't have iptables with the --bpf option, it's going to be a bit boring. You can't do much. Sorry about that. And some details about the previous patch series. And it seems like we are right on time. So do you have any question about that? All right.
If you can share the slides again, you can put the slides in the program later or somewhere.
Yeah, I'll share the slides. So the question was to share the slides. So I'll put the slides on the speaker page on the AHD website, so you have everything.
It wasn't there yet.
Yeah, I'll do. I haven't done it yet. I'll do it. So, all right. Yeah, question?
So,
it's on, yes.
okay.
So, like in every new interesting feature, does it have any drawbacks besides that it requires a lot of efforts to implement all this stuff?
Drawbacks. So, I'd say yeah. You can't use it in production right now, for example, because you don't have all the UDP matchers, for example. But that's something that will be fixed. If there's something that can't be fixed, a downside, well, on the top of my head, I don't know. But I mean, I'm working on it, so I guess people here are the one that can point out issues, I guess. But it's a great middle ground between writing your BPF program and using iptables. you still use the interface you used to, and some people have a lot of rules, and some companies still use iptables with a lot of rules. And you basically get performance for free, so that's nice. One of the downsides would be that, I guess if you stick to iptables in your infra, you probably have an old kernel and an old distro. And currently, if you want to use bpfilter, sorry, you need to use BPF Netfilter program, which are from 2 months ago.
Yeah, thank you.
All right, I guess that's it. So thanks, everyone.